The Federal Aviation Administration's Aviation Safety Program presents the Safer Skies Aviation Training Series. The Safer Skies agenda originated in 1998 when the administrator and her team identified the most critical and most common causes for aviation accidents: aeronautical decision-making, weather, loss of control, controlled flight into terrain, survivability, and runway incursions. Together, these six make up the majority of all general aviation accidents. We encourage all airmen to view all six presentations. The FAA's primary goal is reducing fatal accidents, and that's a responsibility we all share. Let's take the time to focus our attention on these six critical subjects. Hello, my name is Ralph Hood, and I'm the original Top Gun pilot. Actually, that's not true. In fact, half my lies aren't true. I'm an aviation humorist. But today I'm here to talk seriously about aviation safety and the FAA's initiative called Safer Skies. You know, as pilots, we don't start our flying careers or even today's flight with total disregard for good judgment or good flying skills. But along the way, mistakes are made, bad habits are learned, good judgment is left behind on the ramp, and all too often, a few souls are lost in the ink of the morning headlines. It's our intention to help you and all of us find the way to truly safer skies. You know, Bill Gates couldn't calculate all the mistakes and judgment errors that I've made in my 34 years of flying. But I have lived to tell about it, and it's our intention to help all of us identify the issues and the solutions that will make us all better aviators. The Safer Skies program in general is about identifying risk issues and doing something about them. Our ultimate goal is to reduce the number of fatal accidents in aviation. So how do we do that? The first step in any problem-solving procedure is to recognize the problem and identify the reasons it exists. Well, today's program is about weather as it relates to aviation. I'm here to tell you folks, we do have a problem. The NTSB has determined that 27% of all aviation accidents are weather-related. And listen to this, 90% of all weather accidents were caused by pilot error, deficiencies in pilot judgment, and shortcomings having to do with any number of other problems of pilot origin. Now, folks, this is something we can change. So while this particular program is about weather, it's more specifically about how to plan for weather and deal with weather in the course of flight. Knowing meteorology and how to read a terminal forecast are part of the solution, but the bigger part is how to manage that information. Additional Safer Skies programs will deal with some of the other important safety issues. This initial series will address six. This one, of course, is weather. Then there's aeronautical decision-making, loss of control, controlled flight into terrain, survivability, and runway incursions. Obviously, some of these topics do overlap, and in no way do these topics cover the entire range of issues relative to aeronautical safety. But as an ancient Chinese proverb states, a journey of 1,000 miles begins with a single step. You might be thinking, what does this all mean to me in the left seat as I try to work my way around a weather hazard area? I think you'll quickly agree that basic ADM, aeronautical decision-making issues, are at play throughout the entire process of planning and executing a flight, and that adding the weather factor into the equation just exaggerates the need for sharpening both your flying and your thinking skills. A key point to remember here is that it is not weather that crashes airplanes. It's pilots making bad decisions about weather. ADM is defined as a systematic approach to the mental process used by pilots to consistently determine the best course of action in response to a given set of circumstances. Another way to look at ADM is controlling the errors. Error management within the aeronautical decision-making process relies upon situation awareness, problem or threat recognition, and good judgment in resolving the threat or the error. A simple way to apply the decision-making process is the 3 P's: perceive, process, perform. Take in all of the available information like this. Figure out what to do with that information and then do it. After the perform step, evaluate the outcome of your action, which starts the 3P process all over again. Perceive, process, perform. That's a good formula to remember whether you're flying IFR across the country or taking a quick Sunday afternoon hop around the pattern. So let's get started on our weather program by visiting with Mr. Steve Brady. Now, Steve is a veteran flight instructor, but he is so much more. Steve now works for the FAA's Orlando, Florida Flight Standards District Office. Steve has been a safety program counselor for the FAA's Wings program for a number of years.
I'm Steve Brady, and twice I've been honored with the CFI of the Year Award from the Orlando Flight Standards District Office. In 16 years of flight instruction, I have always considered weather to be absolutely one of the most critical to flight safety items. In a recent 5-year period, there were 9,087 general aviation accidents in an estimated 138 million flight hours. That's one accident for every 15,000 flight hours. Of these 9,087 accidents, 1,716 were fatal, or roughly 19%, resulting in 2,976 deaths. I apologize for all the facts and figures, but it's important for us to all understand exactly how dangerous weather can be to aviation safety. On average, 27% of all GA accidents are weather-related, so approximately 2,450 of those accidents, or 490 per year, relate to weather. The trend is that 30% of weather-related accidents are fatal. Do the math, and we lose close to 254 souls per year. That's 254 deaths per year that can be attributed to weather and pilots' inability to cope with the conditions and circumstances. The best news I can offer is that the majority of weather-related accidents occur in VFR conditions and are not fatal. A good deal of those are mishandling crosswinds on landing, stick and rudder 101. Though any accident is a concern to us, we're going to concentrate on the more serious issue of the more serious accidents. Let's break 10 years of fatal accidents down by scenario, and you'll see what I mean. Loss of control on landing, or takeoff due to the pilot's inability to manage adverse winds, accounted for the largest single category of the total weather accidents, about 50%. But of these, only 21% were fatal. That is, of course, a number which does concern us. However, when we look at VFR into IMC, which represents only 10% of all weather-related accidents, we see that over 80% of those were fatal. This indicates that VFR flight in IFR conditions is a very dangerous scenario in a situation we can avoid with proper planning. Certainly in some of these situations, mechanical failure, like power plant, vacuum, and electrical, played a part, but less than 6% overall. That leaves us with a grim fact that pilot error accounts for 94% of weather-related accidents a year. Let's let that settle in for a minute. 94% pilot error. The solution on paper is really quite simple: knowledge, training, and discipline. The real world, however, is considerably less perfect than the hypothetical. Let's break down knowledge, training, and discipline to find some answers. Knowledge. There are two kinds: common sense and education. Common sense, you either have it or you don't. If a prospective pilot doesn't have it, he or she will probably never make it past a respectable CFI or FAA examiner. The system can certainly fine-tune and expand one's inherent common sense, but it really can't be taught. We do, however, have greater control over a pilot's formal education and training. The initial process of earning a certificate, any certificate, is no cakewalk, and the later ratings, commercial, instrument, ATP, etc., are just that much more demanding. And once a certificate or rating is earned, it doesn't stop there. Most general aviation pilots unfortunately don't spend enough time and effort to hone and polish those skills. And far too many ignore the educational programs sponsored by the FAA and various other groups and organizations. Learning is difficult enough, remembering is even tougher. That's why there's so much emphasis on checklist, recurrent training, and continuing education. Being a good pilot is a whole lot more than being a good stick. The more you know, the better you'll be. Training. Before you were granted the privilege of solo flight, you were trained to fly the airplane. As each rating filled in the blank space on your certificate, you were trained in a new aircraft, environment, and situation. Competency checks and recurrent training are not only a fact of life in aviation, they're an opportunity to boost both skill and confidence. Are we providing adequate training? You bet. Is the flying community benefiting at the optimum level? I think yes on the professional level, so why not here in GA? GA pilots, just like the professionals, owe it to themselves and their passengers to be as safe as they can be. Constant training is the key to that commitment. Discipline. Airlines, the military, most corporate flight departments, Part 135 operators, fractionals, and insurance companies require recurrency training and continuing education. The vast majority of general aviation pilots stop training with their ratings and their biannual flight reviews. And though all the training in the world is no guarantee that every single flight will be perfectly safe, it sure puts the odds strongly in your favor. Participate in the FAA's Wings program. Take the time to review some of the excellent refresher courses available on the market. Turn off the TV and pick up your old aviation weather handbook and see how much you've forgotten. There are lots of ways to improve your knowledge and your skills, but it all begins with your commitment. This goes back to the heart of the Safer Skies Initiative. Our number one priority is to prevent fatalities. We all do that by recognizing the threat or the error and doing something about it. Since the subject here is aviation weather, let's visit with Dr. Chris Herbster of the faculty at Embry-Riddle Aeronautical University's Daytona Beach, Florida campus.
Hi, I'm Dr. Chris Herbster. My subject is meteorology. There are two key elements that have to come first if we're going to make aviation safer with respect to weather. First, we have to get the information to the pilots. And second, the pilots have to understand exactly how that weather is going to affect their flight. So let's talk for a minute about what's available as weather information. The FARs are not very specific about where you have to get your weather for Part 91, General Aviation Operations, but the phrase appropriate sources shows up several times. If we look at Part 135 regulations, what the professionals fly, the requirement specifies information generated by the National Weather Service and the FAA. Though there are only a few official sources of aviation weather, there are many other references that might help you as a pilot piece together the entire picture puzzle. Officially, there are DUATS, DTN, and WSI on the internet. Flight service stations, either automated or conversation with a flight service specialist, National Weather Service, air routing traffic control centers, and TWEB or AWOS or ASOS, either by phone or radio. Unofficially, there are newspaper, television, radio, lots of internet options, your cousin Bob, and sight, sound, smell, and touch. The appropriate sources are products of the National Weather Service, the Aviation Weather Center, and their parent organization, the National Oceanic and Atmospheric Administration, along with the Federal Aviation Administration. These organizations provide products designed and tailored for aviation purposes, prepared by folks whose business it is to create useful and discernible information for pilots. Cousin Bob might know it's going to rain when his trick knee starts acting up, but that's not going to help you a whole lot while you're trying to circumnavigate a weather system on your way to Cincinnati. So what do you need to know? Well, that sort of depends on what kind of mission you're on. If you're headed 25 miles away for that $100 hamburger on a Sunday afternoon, a little info about wind, visibility, and developing weather is probably enough. But in these days of heightened security, I wouldn't taxi to the gas pumps without checking the NOTAMs. Technically, when you leave the vicinity of the airport, you're under the auspices of FAR 91.103. But if you're headed 600 miles on an IFR flight plan with a couple of weather systems and maybe a mountain range between here and there, you better not only have all the available current information, but you need to know what the information means and how to use the information. Legally, FAR 91.103 has the same regulatory requirements for both flights. That is, each pilot in command shall, before beginning a flight, become familiar with all available information concerning that flight. This information must include A, for a flight under IFR or a flight not in the vicinity of an airport, weather reports and forecasts, fuel requirements, alternatives available if the planned flight cannot be completed, and any known traffic delays of which the pilot in command has been advised by ATC. There's more to this reg, but this is the part that relates to weather. A little later in the program, my friend Ed Leonard is going to explain what's available as weather information. I'd like to concentrate on the actual weather phenomena and how it affects your flight and your safety. The key areas that affect safety the most are turbulence, convection, icing, and obstructions to visibility like haze, fog, clouds, etc. These are all local phenomena, but they're associated with larger scale features on a weather map. As a meteorologist, I like to look at the big picture first, and then narrow down to the local scale and issues. The biggest features that we are concerned with would be frontal boundaries between the air masses. What's an air mass? Simply, a large volume of air that has more or less uniform temperature and moisture characteristics at any given level. On a weather map, we would recognize these as areas of high pressure. Fronts are simply the transition zones from one air mass to another. We define the word front by the movement of one air mass into a region currently occupied by another air mass. Simply, a cold front is where a cold air mass is replacing a warm air mass. A warm front, vice versa. Generally, a cold front is associated with more unstable conditions, like convective activity, while a warm front is mostly associated with more stable conditions, like stratus clouds. Lots of IMC, but not too bumpy. However, this warm frontal region may be more likely to have conditions of icing, fog, or other low-level obstructions to visibility. For airframe icing, the first thing we need are temperatures near 0 degrees Celsius or below, and the second thing we need is the existence of liquid water, like we find in clouds and light rain. There are volumes of information available about the physics of icing conditions, with terms like supercooled droplets, but what you need to know most as a pilot is that any time the outside air temperature is less than 2 degrees Celsius, watch out. Now, when it gets really cold, say minus 40 degrees Celsius, the risk of icing drops to near zero, as liquid water no longer exists at these cold temperatures. For most applications, you won't see dangerous icing conditions below minus 20 degrees Celsius. Two kinds of ice, rime and clear. Rime ice occurs when droplets rapidly freeze upon striking an aircraft. The rapid freezing traps air and forms a brittle, opaque, and milky-colored ice. Rime ice grows into the airstream from the forward edges of wings and other exposed parts of the airframe. Generally, rime ice occurs with greater frequency than other ice types at temperatures that are colder than minus 15 Celsius. Although rime is the most common type of icing, it is regarded as the least serious since it typically forms at the leading edges of the aircraft where the de-icing devices might be installed. Its shape and texture are relatively ineffective in disturbing the airflow, and its brittleness makes it easier to remove. Some aircraft are certified to fly into known icing conditions if they have certain anti-icing or de-icing equipment. And having the right gear does not get you a free ticket home. Even rime ice can build faster than the anti-ice and de-ice equipment can handle. In clear ice formation, only a small portion of the drop freezes immediately, while the remaining unfrozen portion flows or smears over the aircraft's surface, gradually freezing. Since few air bubbles are trapped during this gradual process, the end result is ice that is less opaque and denser than rime ice. The ice can appear either as a thin, smooth surface or as rivulets, streaks, or bumps of clear ice. Clear ice, sometimes referred to as glaze ice, is generally expected at temperatures warmer than minus 15 Celsius, with most of the reports occurring within the range of minus 10 Celsius to just below 0 degrees Celsius. Clear icing conditions exist more often in an environment with higher liquid water contents and larger droplets which freeze more slowly. Clear icing is a more hazardous ice type for several reasons. It tends to form horns near the top and bottom of the airfoil's leading edge, which greatly affects airflow. This results in an area of disrupted and turbulent airflow that is considerably larger than that caused by rime ice. Since it is clear and difficult to see, the pilot may not be able to quickly recognize that it's occurring. It can be difficult to remove since it can spread over a part of the airframe's surface that is not protected by de-icing or anti-icing equipment. A type of clear icing that is especially dangerous to flight operations is ice formed from supercooled large drops, SLD. This icing occurs in freezing rain or freezing drizzle situations where large supercooled drops can accumulate rapidly and run back along the airfoil. Its lumpy texture can cause severe airflow disruption, and anti-icing or de-icing equipment will have a hard time keeping up with the accumulation. You also need to know the different severities of icing conditions, whether you're interpreting a report or offering up a PIREP. Trace is when the rate of accumulation is slightly greater than the rate of sublimation. Light is when the rate of accumulation may present a problem if flight is prolonged, say over an hour, in this environment. Moderate is when the rate of accumulation is such that even short encounters become hazardous and use of anti-icing or de-icing equipment or diversion is necessary. And severe is such that anti-icing or de-icing equipment fails to reduce or control the hazard, and immediate deviation is necessary. If ice does happen to form, your logical choices are turn 180 degrees, ascend, or descend. You might first think that the air below is naturally warmer, but that won't be the case if you're flying into the region of a warm front, where the air below will probably be colder, while the air above might be warmer. This would be a good time to know exactly where you are relative to the front, and also to know cloud tops. No clouds, no moisture, no ice. Another hazard around frontal boundaries is turbulence. Most people think convection when they hear turbulence, but turbulence is also associated with large changes in wind speed and direction. Since fronts are boundaries between two different air masses, there are also boundaries between two different and conflicting wind regimes. When these conflicting winds come together, it's going to get bumpy. If the turbulence causes momentary slight and erratic changes in altitude and/or attitude, it's light turbulence. If it causes slight, rapid, and somewhat rhythmic bumpiness, it's light chop. Moderate turbulence, or chop, is a bump up from light, but the aircraft is still under positive control. Severe turbulence would cause large and abrupt changes in altitude and/or attitude, as well as indicated airspeed. The aircraft may be momentarily out of control. Extreme turbulence violently tosses the aircraft about and may cause structural damage. The aircraft is practically impossible to control. Clear air turbulence can occur hundreds of miles downwind from the frontal boundary or in the lee of a mountain range. A visual clue here might be lenticular clouds with particularly well-defined edges. The ride below those clouds would be the worst. Severe turbulence can also be found many tens of miles downwind of large anvil-topped cumulonimbus clouds with overshooting tops. This is a result of convection that has so much momentum that it rises above the level where it is naturally buoyant. These regions are all tough to forecast, so the best information available for avoiding the bad ride is to check the PIREPs and avoid the area or the altitude. The granddaddy of turbulent environments is the thunderstorm, cumulonimbus. You can, of course, get a pretty bumpy ride in run-of-the-mill cumulus clouds, those pretty little white puffy clouds. All cumulus clouds are a result of unstable, and as a general rule, the sharper the edges of the cloud, the bumpier the ride. But a true thunderstorm, particularly in its developing or mature stage, is truly a killer. Let's examine the life cycle of a thunderstorm. Cumulus clouds that become thunderstorms tend to follow a sequence as they evolve from developing clouds to precipitating storms. In the cumulus, or growth stage, the cloud is occupied with only updrafts. As the cloud continues to evolve, the droplets become too big for the updraft to support them, and the cloud begins to precipitate. At this point, the cloud has regions dominated by updrafts and regions that are dominated by downdrafts. The last phase of the cloud's development is the dissipating phase. At this point, the cloud is dominated by downdrafts throughout. The downdrafts are what can create microbursts and gust fronts, intense and well-defined windstorms spreading outward from an approaching or passing thunderstorm. Many a pilot has been smacked while trying to beat the weather to the field. The biggest danger of these sudden and intense wind columns is wind shear. Rapidly descending air columns approach the ground and spread out in all directions. An aircraft might fly through a 45-knot headwind, immediately followed by a 45-knot tailwind. You can imagine the consequences. When either giving or interpreting a wind shear report, both the altitude of the encounter and the airspeed loss or gain are important. The appropriate action, if landing, is to increase airspeed and abort, period. If taking off, don't. End of story. Obscuration of visibility brings in a whole new set of issues. Keeping it together, straight, and level at altitude is one thing. Add the stress of an approach to minimums in hostile terrain to the equation, and the picture changes. Some of these issues are regional, like dust storms or blowing snow, but all of us have to deal with fog and low ceilings. So let's look at those. Fog is most likely to form in regions of relatively stable air with light winds. These conditions help to minimize the mixing of the lowest part of the atmosphere, and if the air cools sufficiently, then fog forms. Fog is most common at night or early in the morning when conditions are coolest, but in the vicinity of a warm front, fog conditions can persist throughout much of the day. Salt air encourages the formation of fog, and a bank of sea fog can be fast-moving and quite dense. Because of temperature changes with altitude, a fog layer may only be a couple of 100 feet deep. That suckered quite a few pilots into thinking they can find the field on approach because they caught a glimpse of it from above. Low ceilings are often found in similar conditions as fog. In fact, sometimes the low cloud deck is what's left of a deep fog layer that is dissipated at the surface. Of course, one might also find low ceilings in the vicinity of the warm front, and less commonly a cold front. Stationary frontal boundaries, simply a front that moves very slowly or not at all, can provide the best ingredients for low clouds, as the presence of clouds and light rain can keep the lowest layers of the atmosphere quite cool and moist. The good news, bad news with stratus clouds is that the air is generally stable and the ride is smooth. It's just that no one can see. Finally, haze can be an extremely hazardous situation, especially from sunset to sunrise, as it can obscure the horizon and other ground references. Haze can form any time the relative humidity rises above 50% and is most common along coastal areas where the salty conditions support the formation of very small water droplets. The statistics are filled with VFR pilots that have fallen victim to haze obscuration, particularly in the evening on the coast. At the end of the video, we've listed several excellent sources of additional information on weather for aviators. While these are great sources of information available to you while on the ground, when you're in the air, perhaps the best source of information of the current conditions is you, the pilot. The issuance of PIREPs may be the best service that you can provide to your fellow aviators. Not only do PIREPs alert other pilots of the actual flight conditions, they're the best information that meteorologists can use to verify a forecast and modify this forecast if necessary. No one expects all pilots to be fully trained meteorologists. That's why the federal government has created such a fabulous network of aviation weather information resources. What is critical, however, is that each and every pilot at all levels of proficiency and responsibility has a very good understanding of how various weather phenomena affect the safety of a particular flight and what to do to prepare for the situation. Above all, remember that it's not weather that crashes airplanes, it's pilots and their inability to cope with weather. That's what crashes airplanes. A little knowledge can go a long way on the journey to safe flight.
Now you can see why I think a solid understanding of the weather is so crucial to aviation safety. So let's assume that you've learned and remembered everything there is to know about the weather phenomenon. How do you use that information? The first step is to apply that information to the very specific flight you're about to make. This goes back to our perceive, process, and perform model. Gathering the information and understanding the information is the perceive part of the model. but it does you no practical good if you don't interpret that information within the context of your immediate and specific needs, the current flight operation. I teach my students to visualize the weather relative to their specific operation. For example, if the wind is 160 at 8 knots, gusting to 14, and your runway heading is 220, make a mental picture, or better yet, a drawing of exactly where you expect that wind to be coming from and at what force. Now you've covered stage 2 by processing the information, and you know what to expect. The next step is to perform. In this case, make a go, no-go decision. And if it's a go, then crank in a little left aileron, maintain heading while keeping the aircraft firmly on the runway until you achieve the proper airspeed for positive control. We'll revisit the visualization practice after we spend a little time with Ed Leonard of the St. Petersburg, Florida Automated Flight Service Station.
Hi, I'm Ed Leonard, and I'm a flight service specialist with the FAA. When you call St. Pete to speak to a briefer, it's a good chance you'll get me. Since I joined the FAA in 1988, I've served the dual mission of imparting flight conditions and weather information to the pilot population and telling anyone who will listen about the Federal Aviation Administration and the role that flight service plays in keeping our skies safe. The FAA was created in 1958 from the outdated CAA, or Civil Aeronautics Administration, which had its start in 1938. Both organizations can trace their roots to the 1920s and the 17 airmail radio stations along the 2,600-mile transcontinental airmail route. By the late 50s, much had changed in aviation, and the new FAA was mandated to manage information and administration to the entire flying community, and flight service became an integral part of that organization. At one time, there were almost 400 flight service stations around the country, and it was pretty routine for a pilot to walk in and get a custom briefing in person. In that situation, the pilot could see the current weather and radar maps and eventually satellite imagery and discuss them as necessary, leaving with a pretty good picture of what to expect. We still have several of those stations around, but the norm these days is to acquire your weather information from a variety of sources. The more a pilot knows about weather and how to interpret the reports and trends, the less chance he or she has to find himself or herself in an uncomfortable or even unmanageable situation. Unfortunately, not every pilot is a meteorologist, and not every flight is in the same conditions. That's where we come in. We're here to help you interpret and understand current and future weather, and help you make decisions about how, when, and where to conduct your flight safely. This pre-flight weather information is provided by flight service directly to the end user, in this case, the general aviation pilot, in several forms, and can be acquired in a couple of ways. A briefing by a flight service specialist like myself, either by phone, on the air-to-ground radio, in person, or by an automatic user-prompted telephone call to 1-800-WX-BRIEF. In addition, some airports provide weather information through radio frequencies or direct phone lines connected to automated weather reporting systems like ASOS, Automatic Surface Observation System, ATIS, Automatic Terminal Information System, and AWOS, Automatic Weather Observance System, and TWEBS, Transcribed Weather Broadcast. These numbers, if available, are listed in the Airport Facilities Directory published by the FAA, as well as in some commercially published directories like the AOPA Airport Directory, the Primedia AccuQuick, and Flight Guide. These sources, along with the National Weather Service and designated commercial providers, DUATS, DTN, and WSI, are the certified sources of aviation weather in accordance with FAR 91.103 that Dr. Herbster mentioned earlier. When you begin your flight, you have the advantage of sight, sound, touch, and smell to determine the current weather conditions. Normally, you should be able to look around and make a go, no-go decision if your flight is in the local area. When your destination is not in the vicinity of the departure airport, that advantage is no more. If you're contacting flight service for your weather briefing, you'll ask for an outlook briefing if your departure is 6 hours or more in the future. You'll ask for a standard briefing if you have not received a previous weather briefing, or an abbreviated briefing if you just need to supplement the information you received earlier. Let's talk for a minute about other sources. The logical first step is to acquire the big picture, maybe from the Weather Channel, local television aviation weather on PBS, something like that. Sometimes you'll make the go, no-go, or delay decision from that info, but it at least gives you a basis of current and trending weather information, making the in-depth forecast easier to comprehend. If you're planning your flight on the computer, start your flight planning with a satellite view and surface analysis. These are very good big picture tools. Then go to the METAR, the area forecast, and the TAF. Let's look at each one. A METAR is an aviation routine weather report, which can be a combination of automated and observed sources and is the most current, at least every hour, look at the conditions. This one's for Cincinnati's Lunken Field and breaks down like this. First, the four-letter identifier, KLUK, is for Lunken Field, then the date-time group. The 27 is for the 27th day of the month. The 1853 Zulu is the observation time. If the METAR is already sent and the weather changes before the next hourly observation, a SPECI will be generated with the new time. The next set of numbers is the wind. In this example, the first three numbers indicate the direction that the wind is blowing from, and the next two numbers indicate the wind speed. In this example, 5 knots, 350 at 5. The next number is the visibility, 5 with the letters SM denoting statute miles. Then the next RA is rain and BR mist. The ceilings 600 overcast, temperature 09 Celsius, dew point 08, and the altimeter 29906. The aviation terminal forecast, referred to as a TAF, is a concise statement of the expected meteorological conditions within a 5 statute mile radius from the center of an airport's runway complex. TAFs are issued 4 times daily, 0000 Zulu, 0600 Zulu, 1200 Zulu, and 1800 Zulu, and are valid for 24 hours. The last 6 hours of each period are covered by a categorical forecast indicating that VFR, marginal VFR, IFR, or low IFR conditions are expected. Low IFR, by the way, describes conditions of ceilings below 500 feet and visibility less than 1 statute mile. Marginal VFR is 1 to 3 miles visibility and 3 to 5,000 foot ceilings. Here's an example of a TAF for Cincinnati, and this is how it breaks down. First, we have the 4-letter identifier. The next set of numbers indicate the observation time. 27 is the 27th day of the month. 1740 Zulu is the observation time. The next set of numbers is the valid time. 27, again being the 27th day of the month, is valid from 1800 Zulu to the next day at 1800 Zulu. The surface wind, 190 at 4 knots, visibility 4 miles, light rain, mist with 600 scattered, ceilings 2,500 overcast. Temporarily between 18 Zulu and 19 Zulu, 2 miles visibility, rain, mist, and ceilings 600 overcast. From 1900 Zulu, the surface wind 220 at 5 knots, visibility 5 miles, mist, and ceilings 1,000 overcast. The area forecast, abbreviated as FA, is used extensively by flight service and is prepared 3 times daily and 4 times in Hawaii. The area forecast is an 18-hour synopsis of expected weather patterns with a 12-hour forecast of VFR, cloud cover, and a 6-hour categorical VFR, marginal VFR, IFR, low IFR outlook. Let's break one down. We'll look at southern Georgia where our flight is beginning. First, we're looking at southeastern Georgia, where ceilings 1,500 broken to overcast, tops at 3,000, visibility 3 to 5 miles and mist. Between 16 Zulu and 17 Zulu, ceilings 3,000 broken. Between 18 Zulu and 20 Zulu, 4,000 scattered to broken with broken cirrus above, with the outlook period being VFR. Once you're airborne, you've got plenty of opportunities to update the weather picture. First and foremost, you've got your own eyes and ears. Secondly, you may have some pretty fancy stuff in the panel, ranging from a strike finder or storm scope to weather radar to the ability to display current NEXRAD weather via cell phone or satellite. But you've also got the good old-fashioned NAVCOM radio. We invite you to contact us by radio on the en route flight advisory service frequencies on 122.0, which is FlightWatch, or other published discrete frequencies for en route flight advisory service. That's also where you pick up or pass on PIREPs, which are amazingly useful to pilots. You can tune into ASOS, ATIS, AWOS that we'd mentioned a few minutes ago, or you can pick up a transcribed weather broadcast or TWEB, which is broadcast over selected VOR frequencies, as well as available by telephone. These are continuous broadcasts of weather information prepared for a 50 nautical mile wide radius along a route and for selected terminal areas. TWEBs generally contain a weather synopsis, route forecast, and or local vicinity forecast. TWEBs are valid for 12 hours and issued 4 times a day at 0200 Zulu, 0800 Zulu, 1400 Zulu, and 2000 Zulu. Another important recorded broadcast is a HIWAS, or Hazardous In-Flight Weather Advisory Service, with information about thunderstorms or other hazardous conditions. HIWAS covers a 150-mile radius and are broadcast hourly over selected VORs as conditions require. We've sort of rushed through the wide range of weather-related services offered by Flight Service Station and the National Weather Service, but there's much more in-depth information in the Aeronautical Information Manual published by ASA and on the internet. But I think you can see the role of the Flight Service Station and the Flight Service Specialist is all about you, the pilot. Whether by phone, by radio, or in person, it's our job and our privilege to provide you with the most current and most accurate information available to help you make your next flight the safest one yet.
One of the processes Ed mentioned to me that he and other briefers go through is to mentally put himself in the cockpit with the pilot he's briefing and make the virtual trip. That helps him visualize the weather and gives the pilot more information that he can use more effectively. Good trick. I like to teach a similar technique of visualizing the weather that forces you to take a deeper look. This visualization process is an elaboration of the 3P model, and we've come up with a form to use as a tool. You'll find the download opportunity in the links section at the end of this program. First of all, let's think about the 3 phenomena that actually cause the weather: temperature, moisture, and pressure. Some variation of these 3 factors are present in all weather situations, so the logical first step is to learn the facts about these 3 in all 3 phases of your flight: departure, en route, and arrival. This gathering of information is the perceived step of the 3P model. To effectively use this information, we've got to understand what it means. In this case, what will be the actual conditions based upon the weather-generating factors we just learned about? Well, this combination of factors happens to spell out cold front. So what does that mean? Depending on the measure of those factors, that could mean you pass into a few degrees colder but stable air, or it could mean the ride of your life, perhaps the last ride of your life. So here in the process part of the form, we write down what we actually expect to experience, what the actual conditions will be. That takes us quite logically to the next step in the 3P model and the next blank space on our form. This is where we make a decision, take control, effect and action. We might decide to reroute, delay, choose a different altitude, or cancel altogether. We might also decide that everything is fine. But when we reach that decision, it is based upon good solid information and knowledge, and we can proceed confidently and safely. And I've got to say, if I'm not confident, I'm not comfortable. And if I'm not comfortable, I'm not safe. This is a good opportunity to talk about the personal minimums checklist, of which I'm a big believer. How do the conditions stack up against your competence level? Is single pilot night IFR and rough clouds something you're mentally prepared to tackle? The personal minimums checklist allows you to take an objective look at the facts and compare them to your current competency level. If you pass that self-test, launch. If not, consider the options. But let's get back to the last step in the weather visualization process. Let's make a graphic representation of the flight and conditions. In this case, we're going to make a flight from Valdosta, Georgia in a high-performance, non-turbo aircraft, We'll start in good VFR, pass through some fairly interesting weather that includes a cold front and some potential ice, cross some mountains, and land in an intense traffic environment at Cincinnati's Lunken Field. So we filled in our chart with the actual weather generating info at our departure airport, en route, and at our intended arrival airport. The next step is to visualize exactly what we expect to see on this flight based on that information. This is the process part of the equation, and here is where we complete the visualization tool. You can see a web-based version of this tool at the adds.aviationweather.gov website, but I like the fact that the paper form requires a specific response to every question, forcing you to not just acknowledge the information, rather forcing you to make a decision based upon that information. And then you take the completed form with you on your flight to monitor the weather and your situation. Fly a couple times using the flight visualization tool, and you'll be amazed at how many fewer weather surprises you'll encounter along the way. I find this exercise forces me to truly think about not just what the weather might be, but how I'll be dealing with it. The final step is to perform, or in this case, make a decision. Go or no go. Delay, cancel, proceed. In most cases, the decision will be to proceed, but with a specific plan and a much stronger sense of confidence. Is flying dangerous? It certainly can be, but very definitely does not have to be. The tools are all readily available to create and maintain aviation safety. Though sometimes airplanes crash in weather, 94% of the time it's not because of the airplane or the weather, it's because of the pilot. The system does an excellent job training pilots and offering both equipment and information necessary and appropriate for the mission. The all too often missing link is the pilot and how he or she perceives and processes that information and what decisions are made based on all that input. Weather is a fact of life in a pilot's world. The more you know about it, the safer you'll be. Making that tire squeak at your destination is the sweetest sounds you and your passengers will ever hear.
When we take the time to analyze all of the factors involved in safely completing even a simple flight for a short distance, we begin to realize that the responsibilities we carry as pilots in command are not to be taken for granted. The goal should be zero mistakes, no errors. Realistically, that's not possible. But when the technical skills under your control are in hand, and you've minimized the errors, the potential threats are greatly diminished. But at every stage of flight, there are continuing situations that require your recognition, perceive, your decisions, process, and your actions, perform. The 3 P's of perceive, process, and perform should be constant and automatic whenever you're operating in any flight crew capacity. Understanding weather as it relates to aviation and knowing what to do about it are just 2 of the steps in our quest for safer skies.